Maxwell's equations. James Clerk Maxwell put together the major concepts of electricity and magnetism in 1861. He provided a mathematical formalism, and he added the last term to Ampere's law. Nobel laureate Richard Feynman stated, "From a long view of the history of mankind, seen from, say, 10,000 years from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. The American Civil War will pale into provincial insignificance in comparison with this important scientific event of the same decade." Here are Maxwell's equations. You don't need to know them in this form until AP Physics C or University Physics, but they're very nice to look at. And you can see the equations you've already learned in this course in a slightly different notation. Maxwell encapsulated Gauss's law for magnetism, Faraday's law of induction, and Ampere's law, all in a set of 4 equations that govern electrodynamics. Now let's look at the electromagnetic wave. Thus far, we've modeled various observed phenomena of light. Now let's consider the fundamental nature of light. Now we already know that Ampere's law states that a current, which is caused by an electric field, generates a magnetic field. So in essence, an electric field, a varying electric field, should cause a magnetic field. And Faraday's law states that a changing magnetic field generates an electric field. Well, we can put these together, and that tells us that a changing electric field creates a changing magnetic field, and that changing magnetic field creates another changing electric field, which in turn creates another changing magnetic field, and so on. These time-varying fields travel as electromagnetic waves. The electric and magnetic wave segments of an electromagnetic wave are perpendicular to each other and to the direction of propagation. If you look at the diagram below, you will see the electric field oscillates vertically, while the magnetic field oscillates horizontally, and the direction of propagation is perpendicular to both. Note also that both fields have the same wavelength and the same frequency. In the diagram on the right, you can see an electromagnetic wave propagating, and you can see the changes in the electric field and magnetic field vectors as the wave propagates. In a broadcast radio or TV antenna oriented on, say, a vertical axis, electrons are accelerated up and down by a changing voltage. As the electrons accelerate, they create a changing electric field in the z direction, in the vertical direction. This creates a changing magnetic field in the xy plane. These initial magnetic and electric fields propagate to the right along the y-axis and would get really small very quickly due to their 1 over r squared and 1 over r dependencies. But because these are changing fields, they keep creating their partner field, which creates an electromagnetic wave which doesn't diminish. It will just keep going until it's absorbed by some material. Well, it turns out that light is an electromagnetic wave. The solutions of Maxwell's equations showed that the speed of an electromagnetic wave is 3 times 10 to the 8 meters per second. This was also measured to be the speed of light, and it was realized that light is an electromagnetic wave. There's also an interesting relationship between the electrical permittivity and the magnetic permeability constants, which below shows you that the speed of light is related to 1 over the square root of the product of the two. The answer, 3 times 10 to the 8 meters per second. That's the speed of light in a vacuum.